Today, I'd like to talk about cloud and especially fog computing security, and also why is there a need for it. So, in the OWASP top 10 IoT issues, there are stated, for example, insecure network services, and then another good point that is probably rainbow targeting is insufficient privacy protection and a lack of device management and lack of physical hardening. So first, I will start with a short introduction about cloud versus fog computing. Then I will go more into the detail about the rainbow approach to trust. And especially, I will put the focus on trusted platform model in fog application. Yeah, and finally, the presentation will end with a short conclusion and also some challenges. So here we are seeing the big picture about the three technologies. At the very top, we are seeing the cloud layer. Yeah, I'm assuming that probably every one of you heard about a cloud computing platform and what cloud is able to do. Then there is more or less a new approach, a fog layer. And at the very bottom, there is an edge layer. On the right side, we are seeing the processing speed and the response time. So that means basically all the data are produced at the edge layer, and the edge layer is the fastest hierarchy in this whole setup. So yeah, the edge layer produces a large volume of real data that can be processed to some degree. That depends on the performance of the several devices. And for example, yeah, some basic edge layer devices are some embedded systems, some microcontrollers, a mobile phone, and then the data will be sent to the fog layer. The fog layer is in between the cloud and the edge layer, and is also included in the local network of the edge devices. So this gives the benefit that the latency is relatively low. So the fog layer is able to also produce some real-time sensitive data. Compared to the cloud, in the cloud layer, we have some latency, bandwidth, and privacy and security issues. And the attacks on the data, there is a very high security risk between the edge and the fog layer because first of all, security measures are hard to define, and the attack on data is the probability is higher here. So that means we need to be aware that we have a good security architecture and a good security concept behind our rainbow solution. So yeah. The next slide is about fog computing characteristics. I will go in a shortly overview into these characteristics. So the first one that fog computing is providing is a location awareness and low latency. That means fog computing supports the location awareness in which fog nodes can be deployed. So that means in different locations. And in addition, as I already mentioned, it's closer to the end devices, to the edge layer, and it provides therefore lower latency when processing the data of the end devices. Then the scalability, there are large scale sensor networks that monitors the surrounding environment, and the fog provides distributed computing and storage resources which can work with such large scale end devices. Then we have the third point, geographical distribution. In contrast to the centralized cloud, the services and application provided by the FOC are distributed and can be deployed anywhere. And here, you must be also aware that some of the FOC computing devices are also physical attachable, but we will come later on this point why, and that's why also a point why we're using the trusted platform module. And then it also offers mobility support. This is one of the important aspects of FOC application, is the ability to connect directly to mobile devices and therefore enable mobility methods such as locate ID separation, protocols, the Lisp, which needs a distributed directory system. Then, as I mentioned before, real-time interactions are also possible with FOC computing applications. And this provides a real-time interaction between FOC nodes rather than the batch processing employed in the cloud. Heterogeneity. FOC nodes or end devices are designed by different manufacturers and thus come in different forms and need to be deployed according to the platforms. The FOC has the ability to work on different platforms. Interoperability. So FOC components can interoperate and work with different domains and across different service providers. And then we have also online analytics support. And this is an interplay with the cloud, because the FOC is placed between the cloud and the end device, and it plays an important role in the observation and processing of the data close to the edge devices. So in Rainbow, we are trying to reach an open and trusted FOC computing reference application and that our architecture. So, and it also offers the deployment and management of scalable, heterogeneous, and secure IoT devices, and also cross-cloud applications. And it is an enabler for a secure and efficient data storage and processing. So now I will go a little bit into the cloud storage security-related topics today. As you can see here on the right side, I have here tried to visualize the server encryption at the very top, then the user-side encryption, and the most expensive solution with the use of a hardware security module. So first, as today it's commonly known that at least TLS should be used, so that means a transport encryption. But here we have the problem. The cloud has access to all the data, or in my example, I will use the term file. So the cloud can read the whole file that is sent to the cloud. So therefore, to overcome this issue, the cloud can use a server encryption. Here, the keys are stored in the cloud, and the cloud has access to the keys. So this means if an attacker has compromised the cloud and was able to leak the keys, then the attacker has still access to the whole file that has previously been sent by the user. Here, the user can use a user-side encryption. As you can see here, he encrypts the plain file with a key and send it over an TLS channel to the cloud, and the cloud stores the encrypted file on the cloud. But here we have some drawbacks. How is the key management be handled, and how I guarantee multiple device accesses, because the key is for decryption is only known by the user that has sent the file. So therefore, some cloud providers offers some hardware security module solution. The hardware security module creates and stores the keys only in a separated server or on a separated crypto processor. And it offers also crypto operations like encrypt, decrypt, and signing operations. but here this is also not supported by all cloud providers, and it's also quite expensive to use hardware security model. And therefore, I will go a little bit more into detail what the hardware security model is. It can be, as I mentioned before, directly attached to the motherboard, or as commonly done, separated as an own device over the network. And yeah, HSMs are built to protect cryptographic keys. It also offers crypto acceleration through random number generation, then secure storage, and yeah, one huge drawback is it's quite extensive. And imagine if the HSM is on a different server or on the motherboard, you have to be able to do the maintenance, and this is also yeah, a quite expensive job. So now we are coming to the rainbow security approach. Here we are using the distributed, standard compliant, low-cost HSMs named trusted platform modules. And the rainbow security approach enables trust management service and also offers with some cryptographic protocols that are designed and specified by the TCG standardization, some privacy preserving and accountable device authentication. So for the Rainbow Remote Attestation, to be privacy aware, we are using direct anonymous attestation. And for the runtime verifications, we are using a control flow attestation. And the overall network is a secure overlay mesh network called CJDNS. And here we also try to store the keys in the TPM and all the stuff. And this assures us that only trustworthy devices are part of the network. Here I have to try to give you a visual overview about the whole rainbow approach. So on the left side we have an IoT device X, and could be more IoT devices. So, but here it is important, the IoT device X and the fog node A is the same device, but to different timings. So first, the IoT device and the fog nodes going into such called a setup phase where they're doing a secure enrollment of the hardware, of the TPM hardware, and the secure touch configuration setup to the Rainbow orchestrator and service. Then, if this process is done, the fog node together with the IoT devices using some privacy configuration through the establishment of direct anonymous attestation primitives. Then we are also trying to establish a secure private channel and then authenticate the fog devices to another fog device or to some other IoT device with privacy protection. If this is done successfully, then the devices are able to join the mesh network, and the last point is interacting in the system and also some CJDNS routing mechanisms. And yeah, here one main target that we are triggering is we are dealing with a lot of TPM configuration, with a lot of hardware enrollment, and we are using also a variety of protocols, but this will be then discussed by Simone. Now, I will give you an introduction to the trusted platform model. So a trusted platform model is a separated cryptographic coprocessor that is attached to the host platform where the operational system is running. It is connected commonly over an SPI interface, and it is used to protect security critical data. Such security critical data are, for example, keys or passwords, and it is also TCG compliant, and it offers some mechanism to be temper resilient. This means to resist against logical and physical attacks. It has also included an own true random number generator and offers some generic functions, CQ hardware, and cryptographic functions. And here we are seeing such a chip. So how we are using the TPM module. In our Rainbow approach, we are using Raspberry Pi. At this picture, it's a 3P Plus. And here we have an extension port where the TPM chip is located. This is the Iridium. In Rainbow, we are using the SLB 9670. So how is the, or how I enable, or how I use the TPM module together with the Raspberry Pi? First, I have to enable in the configuration the SPI interface. Then I have to do some modification in the config.txt file in the boot folder. And here we have to set the TTM param SPI on, and the overlay is the TPM SLB 9670. And one good thing on the TPM, it's not rocket science anymore, because there are some software stacks available. The first is the TPM2 TSS, and the second one that we are using in Rainbow is the IBM S TPM 2.0 TSS. And the difference here is the TPM2 TSS is implemented the functionality according to the TCG standard. And here the difference between the IBM is that IBM uses the same functionality but with a more easier interface. So then we are coming to the core components of the Trusted Platform model. The Trusted Platform model offers a TPM signing. So this means it signs the signature with a TPM protected key. And the key, as I mentioned before, is temper resilient. Then it also offers TPM bindings. Here, encryption under a TPM key is happening. And then one important part also for the attestation are the platform configuration registers. So a PCR is a TPM register holding a hash value. Here it offers a SHA-1 or SHA-256 hash. The value extended into the PCR can represent the platform state. So suppose the PCR indicates an untrusted state, but an attacker wants to change the PCR to a trusted value. To do this, the attacker would have to construct another message starting with the current PCL value, whose resulting hash was a trusted value. The properties of such a CQ hash is that it is feasible to do this. So then we have the TPM sealing. Here, the TPM encrypts data under a non-microdable key and to a set of PCR values. Then one important part that is extensively used in Rainbow is the attestation. Here, it is a signed report of PCR state for a remote host. So here, the host can decide wherever to trust a service or not. And also for some privacy mechanisms, we are doing the attestation via direct anonymous attestation protocol. So yeah, as I already said, keys are important. in the whole TPM ecosystem. Here I have to try to visualize the TPM key hierarchies that are offered by the TPM 2.0. So we have first a persistent hierarchy and a volatile hierarchy. Hierarchies has some common traits. Each has an authorization value and a policy. Each has an enable flag in the persistent hierarchy, and each has a seed from which keys and data objects can be derived, and the seed is commonly persistent. And each hierarchy can have primary keys from which descent can be created. So first we will start with the persistent hierarchy. The persistent hierarchy is split into a platform hierarchy, an endorsement hierarchy, and a storage hierarchy. The platform hierarchy is under the control of the platform manufacturer, and yeah, it is achieved by the early boot code shipped with the platform. Then we have the endorsement hierarchy. The endorsement hierarchy is commonly under the control of a privacy administrator, for example, an end user. And yeah, one good thing is the endorsement hierarchy and the storage hierarchy can be disabled separately without affecting another hierarchy. And then we have the third and the last hierarchy in the persistent is the storage hierarchy. It is used by the administrator, and the storage hierarchy should be used for non-privacy sensitive operation. And as I mentioned before, the policy and the authorizations value are persistent through reboot. And yeah, there are more than one primary keys, so with different types, for example, storage, signing, binding, certifying, legacy, and also some different algorithms, RSA, ECC, SHA-1, SHA-256. And the last hierarchy is the volatile hierarchy, called the null hierarchy. It has an own unique seed. So here primary and descendant keys can exist, but it has not the opportunity to keep the keys persistent. So that means a new seed is created on each TPM reset, and it can be more or less seen as an ephemeral key. Then we have, I have to try to visualize an attestation, basic idea how attestation with the TPM works. And attestation is a mechanism to prove its identity and to prove a remote party that the operating system and the application software is in the correct and valid state. So here first, the application has a public and a private key. He sends the public key to the TPM. The TPM computes the hash. This is a PCR value, and then it certifies this PCR value with the public key and the private AEK key, attestation integrity key, and sends it back to the application. The application then sends the certifications of the PCR codes to the verifier, and the verifier verifies the signatures and look up the PCR codes, here stated as hashes from A, in the database. And if the PCR code is as expected, then it returns okay, and otherwise it returns not okay, and the platform or the application can then proceed with the normal workflow. So TPM functionality for privacy preserving mechanism. The attestation integrity key is critical. So it could be traced, and therefore various protocols are defined in the TCG standardization according to the TPM, like a privacy CA protocol, and as we are using in Rainbow, the direct anonymous attestation. Yeah, some challenges in the whole Rainbow ecosystem is how we guarantee and implement privacy-preserving mechanism, how that enables anonymity and also the possibility to pseudonymity. Here the difference is pseudonymity, the signatures that are done on the same pseudonymity can be linked, and with anonymity, the device is fully anonymous in the network. So then how we should handle configuration management, and to the variety and the complexity of the protocol, we have also triggered some challenges about implementation and how we're doing the verification. It can be assured that the whole rainbow approach is trustworthy and correct. So yeah, finally, we're coming to the conclusion. So I've tried to state hardware security benefits for fog computing, and I've also shown how the trusted platform module can be an enabler for strong security. And in the whole rainbow ecosystem, the TPM serves as a root of trust. And also the TPM enables privacy preserving mechanisms. So yeah, that was it from my side. Thank you. And yeah, there's probably some time that you can ask short questions, or we can do it later in the discussion phase.
Yeah, so if there's an immediate question, please let me know. I think Claudio, you gave a sign here.
Yeah. So first of all, Ronald, thank you for the very so Raphael, same name with the R. Sorry about that. Anyway, thank you for your nice presentation. Actually, I have a very, very short question. Actually, how many keys can be stored in the volatile and non-volatile memory?
So on the volatile memory, there are up to 3 keys, and in the non-volatile memory, there can be stored up to 7 keys.
Yeah. Okay. Thank you.
Are there any more questions?
Yes, thanks. I have another curiosity. Specifically, what security feature does the TPM include in Rainbow?
So yeah, you're meaning the hardware itself.
Yes.
Okay. So the security logic consists of sophisticated features like including error detection units, a set of sensors for the decaps and all the other attacks, regulators and filters, along with an enhanced signal shield to detect faults, as well as electrical and physical conditions. And I think there are also some initiate alarms to indicate security breaches.
Okay, thanks.
So if there are no immediate questions right now, you can still think about them. We will have plenty of time at the end to go into a deeper discussion.